Okay, so now we're in section 4.5. We're talking about coordinates and basis. Um, so this section is kind of culmination of what we've done in the previous two sections, talking about both linear independence and spanning sets. So let's start with the definition. Let's suppose we have some set S equals v1 through vn, where these are vectors from some vector space V. Then the set S, this set of vectors, is called a basis for the vector space V if it satisfies two properties. It has to be both linearly independent and it has to span V. Now, what is the purpose of a basis? We're going to kind of see that as we move along. But essentially what it's going to do is act as a coordinate system for a vector space. Which is why we're also talking about coordinates in this section. So remember what we do when we talk about spanning sets. If this set spans the set, the vector space V, then what that means is that any vector that I could choose from this vector space V can be represented in one way or another as a linear combination of these n vectors here. So in a certain sense, every single vector in the vector space V can be reduced down to just these n vectors by representing it as a linear combination of those. However, spanning is not quite enough for what we want a basis to be, because we've also seen that in some cases, a set may span an entire vector space, but certain vectors in that vector space may have multiple representations of that exact same, or as linear combinations of those same vectors. So not only do we want every vector in V to have a representation as a linear combination of some set of vectors here, but we would also like that representation to be unique. We would like it to have only one representation as a linear combination of these vectors, and that's where we need the linear independence part of that. So combined, these two properties guarantee that every vector in V has a representation as a linear combination of these vectors, and the linear independence guarantees that that representation is unique. There's only one way to do that. So we're going to see how we use this as we kind of move along, but a couple more terms to talk about here. Finite dimensional and infinite dimensional. So we say that a vector space V is finite dimensional if it's spanned by a finite number of vectors. Now up here, the set S is clearly finite because there's an end to it. It has a total of n vectors or some finite number V or finite number n. So if V had a basis, or at the very least was spanned by some finite set like this, then we would say that V is finite dimensional. But otherwise, if that wasn't the case, we would say that V is infinite dimensional. In other words, if there were no finite set that spans the entire space V, we call that infinite dimensional. In section 4.6, we're going to be much more specific about what we mean when we talk about dimension. And one thing that is worth mentioning here also, even though my definition of a basis uses a set that has a finite number of vectors, there is such a thing as an infinite basis. We're going to look at a couple of them down here. Typically in an intro to linear algebra class, you don't deal that heavily with infinite dimensional vector spaces. A lot of the theorems that we talk about are actually specific to finite dimensional vector spaces, but that is a very rich area of math, the study of infinite dimensional vector spaces, and areas like functional analysis and things like that will take a deeper look at those types of vector spaces, but we don't really touch on those that much in this class. Okay, so we've defined what a basis is. It's a spanning set for a vector space that's also linearly independent. Now the term basis should sound kind of familiar because we've already used that term in a couple of contexts. Specifically these three right here, we've referred to these sets as standard bases, that's plural for basis, for these different vector spaces. So the standard basis vectors I and j span all of R2, but it's also a linearly independent set. IJK is a basis for R3, Remember this E1 through En, we haven't used that much recently, but this is an important basis to remember. This is just a generalization of these two for Rn. Remember, each of these E's represents an ordered n tuple with zeros everywhere except for one coordinate that'll have a 1 determined by that subscript. So for example, E2 will have a 1 in its second component, zeros everywhere else, and so on. Another standard basis that we've looked at in one specific case is a standard basis for the vector space of matrices. We looked at the case of M22 in a previous section, and we found a basis that I called the standard basis. We weren't really talking about bases in that section, but I used the term anyways. If we're talking about the vector space of M by N matrices, then the standard basis for that vector space is going to contain all the matrices that have zeros everywhere except for a 1 in exactly one entry. So this basis, or this set right here, forms a basis for that vector space. The set of the vector space of polynomials of degree n or less, so Pn, has this as its standard basis, and it should be pretty easy to see that any polynomial in Pn can be written as a linear combination of those. A linear combination of these vectors is what a polynomial looks like, right? Now down here we get to these two infinite dimensional vector spaces. Remember, P is the vector space consisting of all polynomials. And notice its standard basis looks very similar to the standard basis for Pn. It's just that there's no end to this one because we don't have a maximum degree that we impose on the polynomials in this space. So there's an infinite number of these kinds of terms. Finally, oh, this is a typo here. Let me fix this. Remember the space R infinity. You can kind of write that in there. R infinity is the set of all, or the vector space of all sequences of real numbers with component-wise addition and scalar multiplication. The standard basis for that looks very similar to the standard basis for Rn, but instead of ordered n tuples, we have sequences with an infinite number of terms in them. So in the case for R infinity, we have a 1 in the first component, or the first entry, zeros everywhere else, then a 1 in the second entry, zeros everywhere else, and so on. You can see this goes on for forever, okay? All right, so these are the standard bases, and the reason we call them that is because for each of those vector spaces, they're in a certain sense the most natural choices for a basis. But as we've also seen, any particular vector space can have many different spanning sets, and many of those spanning sets can all be linearly independent as well. So what that basically says is that any vector space can have lots of different bases. A basis is not necessarily a unique entity within a vector space. So R2, even though it has this thing that we call the standard basis, the set of vectors I and j, R2 can have other bases as well, and they may serve different purposes. So let's take a look at an example of determining whether or not this particular set of vectors from R3 is a basis for R3. So in order to do that, we have two things to verify here. One, I have to determine whether or not this set of vectors spans R3, and I also need to determine whether this set of vectors is linearly independent. I'm actually going to look at that first. So how do we verify if something's linearly independent or not? Well, remember, we construct a linear combination of those vectors. So k1 times 1, 0, 0 plus k2 times 1, 1, 0 plus k3 times 1, 1, 1. And because we're talking about if we're talking about linear independence here, we set that equal to the 0 vector. And now the question becomes, for the k's, for all of these scalars, do they all have to be 0? In which case we have linear independence, or is it possible that there's a non-trivial solution for those? So remember, this generates a system of linear equations. K1 plus K2 plus K3 would have to equal this first 0 here. K1 plus K2 plus K3 equals 0. K2 plus K3 equals 0. And then finally K3 equals this last 0 here. Putting that in the form of a matrix equation, notice I could write that as 1, 1, 1, 0, 1, 1, 0, 0, 1, K1, K2, K3, and set that equal to the 0 vector. Okay, so that means we're looking at a homogeneous linear system, and as we saw in the previous section, when the coefficient matrix on that linear system is square, it's oftentimes more helpful to not necessarily solve for this explicitly, but to use our equivalence theorem. And again, the equivalence theorem says that if we have a matrix form for a linear system like this, and this matrix is square, then this system has only the trivial solution if and only if this matrix is invertible. Well, is this matrix invertible? Right away I can tell you yes it is, because we oftentimes check for invertibility by taking a determinant, but the determinant of this thing would be 1. And I know that because this coefficient matrix is upper triangular. And we've seen that when you take the determinant of any triangular matrix, you just multiply the main diagonal entries, 1 times 1 times 1. So the determinant of this is non-zero, which means we have linear independence. So I'm going to say determinant is non-zero. So linearly independent, okay? You would want to make that a little bit more of a sentence, I guess, in a test or something, but this is just to give you the idea. Now, how do you check for a spanning set? Well, the checking for a spanning set looks very, very similar to this. The only difference is that I take this linear combination and I set it equal to some arbitrary vector, say b1, b2, b3. But what does that end up looking like? I would still get a system of equations that looks like this, but with a b1, a b2, and a b3 here. K1 plus K2 plus K3. Oops, sorry, I'm not writing that correctly. Let me fix that. Actually, yeah, that would have worked. But let's just go straight to the matrix equation. 1, 1, 1, 0, 1, 1, 0, 0, 1 times K1, K2, K3. And instead of setting it equal to 0, the 0 vector, I set it equal to an arbitrary vector from R3, B1, B2, B3. And remember, the idea is that if we can always find some set of scalars K1 through K3, such that this will give us this vector on the right-hand side regardless of the choice of B1, B2, and B3, that would say that this set of vectors spans all of R3. I can make this work for any vector here. But in the language of systems of equations, remember, that's the same thing as saying that this system of equations is consistent for every vector b1, b2, b3. And that is something that also shows up in our equivalence theorem. This system of equations will be consistent for every vector b1, b2, b3 if and only if this is this coefficient matrix here is invertible. We've shown that it's invertible. So that means that we have a spanning set here. And it spans R3. So what we have, by representing this thing as a system of linear equations in matrix form like this, and checking the determinant of that coefficient matrix, we have knocked out both conditions basically in one shot. We've shown simultaneously that we have linear independence and spanning. So that means this is a basis. S is a basis for R3. Okay? There you go. And again, I just want to emphasize this. If this were a test or something, I'd want you to, write these in full sentences. This is a little sloppy, and that's just because I'm trying to give you the idea, and I didn't leave myself quite enough space to write all that. All right, let's take a look at a different vector space. So this time, let's determine whether the set x squared, x plus 1, 3x squared minus 2, 5 is a basis for P2. Okay, now I could take a similar approach, but I wouldn't be able to use the same tools in this example. And the reason for that, back here, what made this matrix form for this linear equation so useful was the fact that the coefficient matrix was square in both of these cases. The fact that it's square means I can use my equivalence theorem to check for invertibility. But in a different case, if that were not square, then I can't use the equivalence theorem. It'd be useless in this situation. So that doesn't mean, starting out the same way is not necessarily useful, but I'm actually going to take a different approach here. I suspect that this set is not going to be a basis for P2. What does it mean if it's not a basis? Well, all that means is that it has to fail one of the two conditions. Either it doesn't span all of P2, or it's not linearly independent. Maybe it fails both, but that's not really important. It just needs to fail one of those conditions for me to say it's not a basis. I suspect that this set is not linearly independent. I think it's linearly dependent. And I could show that by, trying to create a linear combination of these, set it equal to the 0 vector, and then try to find, some non-trivial solution for the scalars. But we've shown we've proven a couple of useful theorems regarding linear dependence that might make this easier. I'm looking at the two of the vectors here, x squared and 5. I have a quadratic term and I have a scalar or a constant term. And then I notice one of my other vectors in this set is actually a linear combination of a quadratic term and a scalar. So that suggests that I can probably write this this one polynomial in this set as a linear combination of the others. Let's see if I can do that. 3x squared minus 2. How can I write that as a linear combination of the other vectors? Well, 3x squared I would clearly put a 3 in front of that x squared there. I don't want to have a linear term. I don't want an x term because there's not one showing up here. So I would make the coefficient there a 0, x plus 1, plus. And then 5, I want that to look like a negative 2. So the scalar I can use there is just negative 2/5 and multiply that to the 5. So these are the other 3 vectors in that set, and I can see that this linear combination will give me the 4th vector in that set. We proved in the previous section that if one of the vectors in a set is able to be written as a linear combination of the others, then the set must be linearly dependent. So I'm going to say set is linearly dependent, and therefore not a basis for P2. Okay? So we have more than one way to either show that a set is a basis or is not a basis, and it's helpful to know all of the tools at your disposal. All right. Let's try for one more here. In fact, I think I'm going to save this one for the next video. But we're going to take a look at a space of matrices and try to do the same thing. Is this a basis or is this not a basis? So that'll be the next video.